Okay, y'all, I thought I'd hop on here real quick and work through this activity that we did together in class. Hopefully I'll be able to work through it a little bit more slowly and have a little bit more time to explain some things. So for today, you're going to need the ionic bonding activity sheet, and you're going to need your colorful periodic table that we've colored, showing the red metals and the blue nonmetals, as well as our valence electron groups and our oxidation numbers for all of our groups. Okay, so ionic bonds. So ionic bonds involve the transfer, I'll zoom in, of electrons from a metal, and I'm actually going to put metal in quotes, or from metals to nonmetals. Okay, so the reason why I know that the metals transfer to the nonmetals is, remember, my metals have these positive oxidation numbers, meaning that when they form ions, in order to feel stable according to their octet rule, they're going to lose their electrons. Well, who are they going to lose their electrons to? The nonmetals. And that makes sense because over here our oxidation numbers for nonmetals are negative, which means they gain. So here we have my metals tossing their electrons over to the nonmetals. The reason why I put metals and nonmetals in quotes is because we now know we have these things called polyatomic ions, and some of the polyatomic ions have negative charges, right? And so if they have a negative charge, that is showing them gaining an electron, which means they can be one of the components or one of the key players in forming an ionic bond. Similarly, I've got a metal acting polyatomic ion in ammonium, so that means he can also act as a metal. So basically anybody on the periodic table who makes an ion positive or negative, or one of my polyatomic ions, can be involved in this ionic bond. So basically what I'm looking here for is anything that can make a positive charge and anything that can make a negative charge, which is super exciting. Okay, so it says, draw the electron diagram for each of the following elements. Use the symbol for the element and the number of dots corresponding to the number of valence electrons in each element. Okay, so we've done this before. We know that sodium, y'all, he is in group 1 right here. We know he has 1 valence electron, so we would show him with an electron dot diagram with just 1 dot. Magnesium, he's the next guy over, second group, so Mg with 2 dots. Oxygen, oh my gosh, we have zipped on over oxygen, you guys. He is right here in group 16. That means he has 6 dots. 2 of them will be paired up, right? Fluorine, he's a halogen. He's in group 17, so he's got 7 valence electrons. So only 1 is not paired up. And then finally, neon. Neon's my noble gas, right, you guys? So neon is going to be in group 18. He's going to have a full valence shell, a full octet of 8. So this is kind of a review. I'm going to go real quickly through the next row of examples. In the next row of examples, you'll probably notice, oh, she's making me do elements in the exact same groups, which I'm like, yeah, I am. So potassium is also a group 1 representative. Calcium is a group 2 representative. Sulfur, group 16 with 6. Chlorine, oh, I wrote oxygen, you guys. I was looking at my picture above. Chlorine, Cl, he's a halogen. He's group 17, just like my fluorine. And then argon, also a noble gas. So the follow-up question is perfect to kind of look at this little dot diagram situation we just did of elements in the same group. It says, what conclusion can be made about electron dot diagrams for elements in the same group? Y'all, they have the same number of valence electrons. So we could write, they have same number of valence electrons. The second part of the question says, well, what is significant about this? Why does it matter that we have same number of valence electrons? What does that do for us? Well, therefore, since we know electrons are what is involved in all of chemistry, we know that they're going to have similar chemical properties. So therefore, similar chemical properties. Yes. Okay. Now, this chart's going to be real cute, real easy for us to do. Hopefully will not take very long. It's finding all these elements and giving me information about number of protons, group number, number of valence electrons, and an oxidation number. Chlorine, he's in a halogen group. We know that his atomic number is atomic number 17. So if he is atomic number 17, that lets me know that he has 17 protons. The group that he is also in just happens to be 17. That is just purely coincidence. Those two things are not going to be related. Valence electrons, 7, which means his oxidation number is a -1. Beryllium, group 2. Beryllium, group 2 right there. He's got number of protons of 4, because that's what his atomic number is. Group 2, which means he has 2 valence electrons, which means his oxidation number is a +2. He will lose those 2 valence electrons to make a cation. Fluorine is going to be atomic number 9. He is also in the halogen, so he is in group 17, which means he will also have 7 valence electrons, just like chlorine, form a -1 charge. Then we got lithium. Lithium, he is in group 1 with my alkali metals. He is atomic number 3. So 3, and then we got group 1, and then our valence electrons, we have 1 valence electron, and then my oxidation number is +1. That means that he loses that 1 valence electron. Oxygen, group 16, oxygen is atomic number 8, so he's got 8 protons. He's in group 16. Everybody in group 16 has 6 valence electrons, and in order to achieve his octet, he gains 2, so he forms a -2 charged ion. And then finally, phosphorus, he is atomic number 15, also happens to be in group 15, which is super exciting. So 15 in group 15, everybody in group 15 has 5 valence electrons, which means they gain 3. So phosphorus and everybody in group 15 will form a -3 charged ion. So that was super fun. Now let's go to the back of this page. This was all like a little bit of a, y'all learned this stuff before basically. Now let's apply this in terms of how do I make ionic bonds with this stuff? Okay, and it says follow your teacher's directions to complete each ionic bond. So now you'll follow your teacher's directions. So here I'm wanting you to make a bond between lithium and fluorine. Does that make sense? Lithium and fluorine. Yeah, a metal and a non-metal. I have the option to do that, right? Okay, because that's a metal and a non-metal. We know that that's going to look real good for us, making an ionic bond between a metal and a non-metal. So the way that we're going to demonstrate what an ionic bond would look like is we're first going to draw each one of these elements as we drew them over here. They're electron dot diagrams. So lithium, we knew he was in group 1. He's got 1 valence electron. And then we got fluorine. He's in group 17, which means he's got 7 valence electrons, you guys. Okay, so now looking at this, we know we wrote on the front of this page that ionic bonds transfer their electrons from the metal to the non-metal. Okay. Well, lithium has 1 valence electron. Can he transfer that to fluorine? And in the process of transferring that electron to fluorine, will fluorine be happy? Yes. Fluorine will have gained all 8 electrons that he needs to feel happy and stable with his octet, and lithium will have successfully gotten rid of his valence electrons in order to have his full shell underneath already full. So yeah, this is a perfect ionic bond. I'm liking this. So this showed what our thinking process was, but what we're going to show over here is the result of this transfer. That result of the transfer is the ionic bond, because if you'll remember, an ionic bond is the electrostatic attraction between this now positive cation and the negative anion. So let's show them as positive and show them as negative. So lithium, remember when we draw our cations, none of those dots exist anymore. We give him brackets and we say, bam, he is positive because he has lost his 1 electron. And then we're going to show fluorine. He's now got all 8 from that transfer. So we are going to show that. Put brackets around him saying, hey, he got that by gaining an electron from what he normally did. Y'all, this is the ionic bond. I have a positively charged cation. I have a negatively charged anion. You guys, and this is the ratio of each one of these ions that I need to each other. I only need 1 lithium for every 1 fluorine. Having 1 lithium and 1 fluorine was perfect. All of the electrons got lost where they needed to get lost. All of the electrons were gained where they needed to get gained. So in fact, the ionic compound that we've created between lithium and fluorine is LiF. I have 1 lithium and I have 1 fluorine. We would call this, you guys, this is a preview for our naming that we're about to get into. This is lithium fluoride. Congratulations, we've made lithium fluoride. Let's hop on down. Let's do the next. Okay, I'm asking you to make an ionic bond for us between beryllium and iodine. Well, first of all, does she give me a metal? Does she give me a non-metal? Let's see. Beryllium, yep, he's a metal in group 2. So I can go ahead and write Be. And remember, he's got 2 valence electrons. They're unpaired. And iodine. Iodine, he's way down here in the halogens, but he's halogen, so he's group 17, 7 valence electrons. So let's just put an electron dot for each one of those. Okay, all right, so looking at here, it looks like beryllium, he got to get rid of 2 valence electrons here. Well, he can give 1 to iodine, but he can't give the other one to iodine because after he gives the first one, iodine is like, I'm happy, thank you, you may not give me any more. So what does beryllium do? Maybe he needs another iodine. Okay, let's put another one on here and see what we're going to do. So here's another iodine. Yeah? Well, what about beryllium's second valence electron? Comes over here and satisfies another iodine. Yeah, I think that works pretty good. Y'all, this is what is required for beryllium and iodine to pair up together. You need 2 iodines for every 1 beryllium. Okay, so let's show the result of this transfer. Let's show that cation and the anions that we've created. So beryllium has lost his 2 valence electrons, so we will show him as that. And now I've got 2 iodines. Each one will totally have 8 dots. And each one gained 1 from beryllium. So that's a negative right there. So here's my second iodine. Yes. Okay. Y'all, we just made another ionic compound. So if I wanted to, I could write a formula for this, but it's going to look a bit different than what I did up here because I don't have 1 of each. I actually have 2 iodines for 1 beryllium. So we're going to represent that in the chemical formula. We're going to be like, hey, BeI2. Congratulations, you guys. We've just written the formula for beryllium iodide. That's awesome. Okay, let's move on to the third one because this is getting kind of fun. It's like a game. Okay. Lithium and oxygen. We've seen lithium before. We know he's in group 1, so he is absolutely a metal. Oxygen, where are you at? Oxygen is right here in group 16, right? So he's got 6 valence electrons. Okay, so let's look at everybody here. We got lithium with his 1 valence electron, and we got oxygen with 6. Okay. Now, lithium, we know he's going to get rid of that valence electron. Boom. Lithium is happy. He's like, bye, see you later. But is oxygen happy? No, he's like, I need 1 more, thank you. Well, who's he going to get another electron from? How about another lithium? Yeah, we can bring another guy in here. Yeah? He's got his valence electron, and he's like, oh my gosh. So maybe if I ask lithium and oxygen to bond together, I got to have 2 lithiums for every 1 oxygen. So the result of that ionic bond is we're going to have 2 lithiums, each with a positive charge, because they each have lost 1 electron, right? And then we're going to show oxygen. And oxygen is going to have a -2 charge because he gained 2 electrons from each one of the lithiums. So here we go and write a formula again, except I got 2 lithiums for every 1 oxygen. So in my formula, I got to show that ratio. I got Li2O. So guys, this is the formula for lithium oxide. Lithium oxide. We love this. In fact, if we want, we can box off our ionic structures. think that's a good idea. Because the purpose of this activity is get to draw these pictures. This is what I want to see. But I love the work through of this process because it helps us plan, well, how many of each atom do I have of each type? That will complete the octets for everybody involved. Okay, last little problem, super fun. Aluminum and chlorine. Let's see. Aluminum, yup, he's in group 13, so he's got 3 valence electrons. So Al, 1, 2, 3. And we've got chlorine, group 17, 7 valence electrons. We're ready to go. I'm super excited about this one. It's going to be fun. 1, 2, 3, 4, 5, 6, 7. Okay. All right. So we know metal transfers to the non-metal. We were like, cool, sounds good. All right, aluminum, boom. That chlorine is happy. He's like, see you later. Aluminum's still got 2 other valence electrons that he needs to get rid of for him to be happy. So what will he do? How about we get a little bit more chlorines in the mix? Specifically, how about we get 2 more chlorines in the mix? In other words, we're going to have a total of 3 chlorines to go with this 1 aluminum. And it does not matter which side of the chlorine you put the single unpaired electron. In fact, I probably should have been a little bit more strategic about where I put my unpaired guy, because now I'm having to do like a big circumnavigating around here. Okay, so that's the transfer. So 3 chlorines will gladly be able to accept those 3 valence electrons from aluminum. So the result of this, you guys, the ionic bond, is that aluminum has lost 3 valence electrons. We got +3 charge, no dots on him. And now I got to draw 3 chlorines with 8 dots around each one of them. So that's a lot and super fun, and oh my goodness gracious. But each one, after he's a full shell of 8, give him a bracket and give him a charge of a -1. This is nutso business, you guys. Okay, so much things. So many chlorines, so many dots. Y'all think this dot situation is a lot. We're about to get to covalent bonding next unit, and then y'all gonna be dotting like it's nobody's business. Okay, so yes, okay, you guys, we have drawn aluminum chloride. But writing his formula, we need to show you the ratio of each metal and non-metal and how many of each you have. I have 1 aluminum, Al, and I got 3 chlorines. So AlCl3. That's your formula for aluminum chloride. Okay. So I love mapping this out because it shows you how to draw these Lewis dot diagrams for my ionic structures, and it also is about to help explain when we get into being able to write our own formulas without having to do all this first, okay? I'm excited.